In this section, we'll take a look at the Ospf concepts objective of the JNCIS Service Provider exam. We'll examine neighbour formation, designated routers, and the different LSA types. For more detailed coverage of this objective and more, please check out the JUNOS Intermediate Routing course.
In this section, we're going to have a look at some of the fundamentals of Ospf and the packet types that underpin its operation. So first and foremost, what's the purpose of Ospf? Well, it's there to find the shortest path to all the destinations that it's aware of. In fact, the name Ospf stands for Open Shortest Path First. So first of all, how does it operate? Well, we can think of Ospf as a distributed database system. So each router that's participating with Ospf is going to have a database of IP destinations within the network that's configured to speak Ospf. And these distributed databases are populated using link state advertisements. Link state advertisements, there are many different types, but their core function is to describe networks that are present within the given Ospf domain. So routers within a Ospf network send link state advertisements, send LSAs, and these LSAs are used to build local databases on every router that's speaking Ospf. And so this database then consists of the links that interconnect the different Ospf speaking routers and the destinations that can be found behind those Ospf speaking routers. So against this database, we then need to determine the best way to get to those given destinations. And this is where the SPF algorithm, sometimes called the Dijkstra algorithm, comes into play. And this algorithm runs against that database to find the shortest paths to all the destinations contained within it. The exact operation of this database is beyond the scope of this video. However, if you just think of the algorithm starting off, and what it's doing is it's routing a tree at the router to which it's operating against, and then it's building branches, the shortest path branches, to all other destinations, all other routers within the network, onto that tree that's routed against itself. And if you go on to future Juniper courses, this algorithm will be explored in a lot more detail. So this is the core functioning of Ospf. Let's have a look at the different packet types that facilitate its operation. So first we have the hello packet. This is sent to a multicast address, and it's used to discover what other Ospf speaking routers are connected, and it's also there for state maintenance of an adjacency once that adjacency is established. We then also have database descriptor packets. Database descriptor packets are used to tell neighbouring routers exactly what the local database, that database of LSAs that we talked about earlier, consists of. So we can tell our neighbours what our database looks like. Our neighbours can tell us what their database looks like, and we can synchronize them to bring them in line with each other. So that's database descriptor packets. The next packet type is a link state request. And a link state request is what we're going to use to bring that database in sync. So if we discover that our database is not in sync via database descriptor packets, we then request pieces of the database, the LSAs that we're missing, from our neighbours using link state request packets. Then we have the link state update packets. These link state update packets are what actually contain the LSAs that are describing the destinations within our Ospf network. So these are what are actually exchanged that then brings our database in sync with our neighbours. And then finally, we have link state acknowledgement packets. And these are used because OSPF implements its own reliable delivery mechanism. So for every link state update that's sent, the neighbor that's receiving it sends a link state acknowledgement to tell the sending neighbor that he's received the update. If the update is not acknowledged, it will be resent. And so with these 5 different packet types, we exchange these different packet types, and then we move from having no neighbor adjacency to that neighbor adjacency being fully established. And we step through various different stages when this happens. And this is what we have illustrated on the right-hand side of the board here. And these stages loosely map to the packets that are exchanged as part of the process that we're then traversing through. And I'll talk through that in a little bit more detail now. So we start off in the down state, where we're not aware of any other neighbors on the link that we're connected to. The init state is when one hello packet has been received by a neighbor. He then sends a hello packet back. We then get to the two-way state. This is when hello packets have been sent and that the initial sending router has seen a hello packet come back to himself, with himself listed in that packet. He can see his router ID in the packet which he's received. So this is now said to be in two-way state. Once we're in two-way state, we can then move to the xstart state. So this is where we decide the neighbor that's going to be primary for exchanging database descriptor packets. Once we've decided who's going to initiate the database descriptor exchange, we then move to the exchange state, which is where exchanging those database descriptor packets that are describing the local state of our databases. Once we've exchanged the local state of our databases, we can then move to bring those databases into synchronization, which is what happens in the loading state. And in the loading state, this is a series of sending link state requests where we're requesting missing LSAs, the link state updates where we're sending those LSAs that have been requested, and the link state acknowledgements where we're acknowledging the link state updates that have been sent. And once all of these packets have been exchanged and the local and the remote databases are in sync, we can then say that we're in full adjacency state. This is a quick overview of the basics of OSPF and the different packet types. In subsequent videos, we'll explore in more detail the different LSA types that you'll find in a typical OSPF network, and how we can impart hierarchy into our OSPF system to better scale our control plane. In this section, we're going to take a look at OSPF on the LAN. So on a LAN network, it's possible that you will have many different OSPF speaking routers, all interconnected via the same layer 2 LAN network. In this example we have on the board here, we have 5 OSPF speaking routers, all interconnected to the same layer 2 segment. Now, we could have neighbor adjacencies between all of these routers. However, because all of the layer 3 routing is identical, we've just got different layer 2 properties here. We're getting into a situation where we have inefficiency. So to resolve this inefficiency, OSPF has this concept of designated routers and backup designated routers. So what we have is, instead of neighbor relationships between all devices on a LAN network, we have nominated 2 routers, the designated router and the backup designated router, and then all other routers on that segment only have full neighbor adjacencies to the designated router and the backup designated router. Between each other, they have adjacencies, but they have stopped in the two-way state. These routers are said to be in the drOther state. And this way, we're saving on resources in this LAN segment, because we've only got adjacencies to the DR and the BDR. The DR other routers do not have any neighbour relationships with themselves. They only have neighbour relationships to the DR and the BDR. So how do we nominate which routers on a LAN that we want to be the DR and the BDR? Well, we have an election process. And this election process is governed by the configured priority of these devices for this particular LAN network. And this priority can range from 0 to 255. 0 being never become a DR or a BDR, and 128 being the default value. And the highest value of that priority wins the DR role. The second highest priority wins the backup designated router role, the BDR role. All other devices are then in this DR other state. If the priority values are equal, we then tie break on the router ID of the routers in this LAN segment, with the highest router ID winning. This election process is said to be non-deterministic. This basically means that instead of the election to DR and BDR being absolutely determined by this priority, it's also a factor of the time that these devices came online on this LAN segment. So all of these devices, say, come online on this LAN segment, and they perform this election and choose the DR and the BDR. If at a later time some other router is interconnected to this segment that has a higher priority, he does not become the designated router because that election process has been performed and it's finished. He just gets to be in the DR other state. For him to be elected as the DR, we would have to clear all of the neighbour adjacencies on that LAN segment. This scenario of having more than 2 routers on a given layer 2 network is starting to become less and less. And by default, even if you only have 2 routers on a given LAN segment, OSPF is going to perform this election process. And this takes time. We're also storing more state than we would if these were devices were just pure point-to-point on the DR routers. So if your network only consists of Ethernet segments that are acting as purely point-to-point networks, i.e. they're interconnecting routers, and you don't have any switch in between with hosts connected to it, then it's recommended practice to configure those interfaces in OSPF as point-to-point interfaces. This means that when those neighbour adjacencies between those routers come up, you don't have to enforce the DR-BDR election process, so those neighbour adjacencies establish more quickly. And as I've mentioned, it also means that you're storing less state on these devices. So it's a small fine-tuning to make that control plane on these devices slightly more efficient. And this is a quick overview of designated routers and backup designated routers within OSPF. In this section, we're going to examine some of the different OSPF LSA types. So that's link state advertisement types. And OSPF, you should remember from previous videos, uses LSAs to advertise routing information within an OSPF domain. And then routers within that OSPF domain can run an SPF algorithm against that routing information to determine the shortest path to those destinations that have been described in those LSAs. And the LSAs that are used to carry routing information vary depending on the configuration style and the topology style that's been deployed in your particular OSPF deployment. And we'll talk through the various different deployment styles and how they map to LSA types within this video. So the first deployment style is to use a single area within an OSPF domain. And this is by far the simplest version that you can use to deploy with OSPF. We'll examine this first. So imagine that you have deployed a single OSPF area. Imagine that this is just this central area that we've drawn on the blackboard here, this backbone area, area 0. And within this area, you have multiple OSPF routers, all interconnected with various different link types. And within this area, what we're doing is each OSPF speaking router is advertising type 1 LSAs and maybe type 2 LSAs. Type 1 LSAs or router LSAs are describing the links between OSPF speaking routers and the IP addressing and network addressing that's on those links. And if you remember that these LSAs are advertised within OSPF within link state update packets that are sent between an OSPF speaking router and its immediate neighbours. So that's type 1 LSAs. Type 2 LSAs or network LSAs are sent by the DR, the designated router, when there are broadcast and multi-access network links on that given router. And this is because on those types of links, the designated router needs to augment the information that's carried in those type 1 router LSAs with a little bit more information. He needs to tell the rest of the network what other OSPF speaking routers are connected to that broadcast segment. And to do that, he uses these type 2 LSAs. So all of these routers within this OSPF area learn about all of these LSAs via advertisement to each other in link state updates. Another scenario that you could be using with OSPF is that you might be redistributing routes from another routing protocol into OSPF. And we've demonstrated this here on the board with BGP routes coming into OSPF. When you're redistributing external routes from a different routing protocol into OSPF, the router that's doing that in OSPF terminology is said to be the Autonomous System Border Router, or the ASBR. And we carry these external routes in type 5 or external LSAs. And these type 5 LSAs are propagated throughout the area, much like the type 1 and the type 2 LSAs are. So this area now contains consistent databases that are describing all of the destinations within this area and all of the external destinations that have been advertised into it. And this is how a single area OSPF deployment operates. This is great for the majority of use cases with OSPF. However, you might be running a very large network with some routers in that network with very small CPUs, with very limited control plane capabilities. And if those routers were to participate in a very large single area network, their control plane could be overwhelmed with the amount of shortest path first processing and LSA receipt processing that goes on within that single area. So to account for these situations, OSPF has the concept of hierarchy. And this is where we can split an OSPF network into multiple separate areas. And when we advertise reachability via LSAs across area boundaries, we can summarize some of the routing information that's happening within an area as it crosses those area boundaries. And this summarization means that we're reducing the pressure on the control plane of those devices running in those separate areas. So this means that we can scale OSPF out to many more devices, particularly when those devices have limited control plane capabilities. And when we're doing this, we start to use different LSA types. So if we take a look at this example here, so we've got a backbone area. This is area 0 in our case. In proper OSPF terminology, this is going to be area 0.0.0.0. This area is connected to another area, area 1. and routers that interconnect areas within OSPF are said to be area border routers, or ABRs. Now these area border routers are what's performing the summarization of LSAs, and this is what's allowing us to scale the different areas in OSPF accordingly. So type 1 and type 2 LSAs are aggregated together by ABRs, and the information contained within them is instead advertised via type 3 or summary LSAs. So all of the type 1 and type 2 LSAs within this backbone area are summarized together and advertised via the ABR as type 3s into that area. We also need to advertise the external reachability of routes that have been redistributed into OSPF into that area, and we do this via the type 5 LSAs that are propagated into that remote area, and we also augment this information with type 4 LSAs. Type 4 LSAs, or ASBR summaries, just describe to routers connected to other areas how to reach the ASBR that first redistributed that external route. And this summarization, the use of these type 3 LSAs, means that we can scale to much larger numbers of OSPF speaking routers within our OSPF domain. Sometimes this amount of scaling improvements still isn't enough to support much smaller routers that are deployed in very high numbers. So we can take this scaling approach still further, and we can deploy what's called stub areas. So stub areas are much like other areas, the only difference being that the ABRs, the area border routers that interconnect to stub areas, do not flood type 4 and type 5 LSAs. So stub areas only know how to reach destinations within an OSPF domain. They don't know how to reach routes that have been redistributed into OSPF via ASBRs. We can take this scaling still further, and we can have what's called a totally stubby area. And a totally stubby area is also filtering type 4 and type 5 LSAs, but in addition to that, it's filtering type 3 LSAs as well. There's no LSAs being advertised into that area. All we're doing is that we're propagating a default route from the ABR into this area. So we're dramatically reducing the amount of routing information that has to be processed by routers located in a totally stubby area. And finally, there's another area that we need to talk about. That's the NSSA, the not so stubby area. So this is an area that we need to reduce routing information that's flowing into it, much like a stub area. However, it has autonomous system border routers interconnected to it. It's receiving routing information from an external routing protocol. So if we were to approach it much like a stub area, we'd be filtering type 4 and type 5 routes. And we need to be using type 5 routes to carry information from our ASBR to the rest of the OSPF network. So just deploying it as a stub area alone is going to break functionality. So instead we have this special area functionality of the not so stubby area. So we're not allowing type 4 and type 5 routes to flood from the rest of the network into our NSSA. Instead, we are allowing external routes to flow out of our NSSA via a special type 7 LSA. That's the not so stubby LSA. So in this case, the ASBR advertises its external reachability via type 7 LSAs. They reach the ABR, the area border router. He then converts those type 7 LSAs into the type 5 LSAs that the rest of the network can understand. And as normal, this ABR is also still advertising Type 4 LSAs to describe the location of that ASPR router. This is quite a lot of information to take in, but hopefully this now makes it clearer what the various different types of LSA are used for and how they fit into the different configuration deployments that you'll typically see within an OSPF domain.